differences between tasks as well. All right. For our next session, we have Eran Malach speaking. He has some really creative and great work in theory of neural networks. So I'm very excited to see.
Yeah, thanks. Yeah, okay. Thanks for inviting me. So this will be a talk about, I guess, comparing between families of sequence models, focusing on transformers and state space models, and we'll talk about kind of like the benefits and limitations of using these models. I guess we'll kind of start with maybe the kind of basic question. When we want to do sequence modeling or language modeling, what kind of model do I want to use? And if you'd asked this question in the 90s, the answer would probably be some kind of recurrent network or LSTM. So something with kind of like a fixed state or memory that you update from iteration to iteration. This is how we do sequence modeling or language modeling. At least in the 1990s. And then 2017 came, and I guess, this is a workshop on transformers. As you all know, this became kind of the dominant architecture for doing sequence modeling. I'm not going to, I assume everyone here knows how transformers work, so you're very familiar with kind of how they're built and used. But this is kind of a shift in how we do sequence modeling from something that has like a fixed state and is being updated to something that sort of like sees all the sequence at once and does like operations is like across the entire. And then kind of more recently, state space models, which is, I think of it as kind of like a nicer variant of recurrent neural networks, were introduced or reintroduced, and kind of a very recent work on state space models or a model called Mamba really show that they can be trained and can be competitive with transformers. And maybe this kind of brings us back to this kind of recurrent model or architecture that we can use for sequence. So I guess the basic question we want to ask is like, what model do we actually want to use when we're doing sequence modeling? So I will not discuss in detail how the kind of state space model or the Mamba architecture is built, but the kind of main thing that's important for us is basically we have a fixed memory or fixed state, and we update this as we kind of generate it. So I'm not going to get into details of how exactly this is done, but I assume at least some of you are familiar with this architecture. So, okay, which model is better is, I guess, a big question. So one thing that we can kind of like can concretely say is, what is the cost of running the different models? So the cost of running inference with a transformer, I'm sure you're all familiar with this. We're basically measuring the computation and the memory that it takes us to compute the next token in the sequence. And the memory in the transformer grows with the sequence length. We kind of keep a KV cache of all the activations in the past, and the more tokens we produce, the larger this memory grows. And along with it, the compute per token grows again linearly with the sequence length. So the computation overall would be quadratic because each token we pay a linear cost in the sequence length, and the memory grows linearly, right? So I guess this is should be. RNNs or state space models are nicer in the sense that the memory doesn't grow and the compute per token is fixed. So we decide on what's going to be the size of the model, and then we can basically run it forever and things don't blow up. So it's the same amount of memory that we use for generating the next token, which makes the memory fixed and the compute overall be linear with the number of tokens. So far, this is kind of just trying to measure the cost of transformers versus state space models or recurrent models. And there's something very nice about state space models, and I guess this is kind of the main reason that people kind of want to go back to them, is that they're kind of more efficient at inference. But I mean, cost is not the only thing that we care about, right? We also care about performance. And I guess the kind of maybe striking thing about the Mamba paper and the papers that come after it is when you try to measure performance in kind of the standard way, so like evaluate the perplexity or the loss of the model on a training data set, we see that it's kind of hard to read here, but we see that the Mamba model is very competitive, at least for some scales with the kind of state-of-the-art transformer. And when we're evaluating this on kind of standard downstream tasks that we evaluate language models on, we also see kind of very competitive performance. So maybe we just can get the same performance without paying the extra cost of like memory growing linearly with the number of tokens. And this sounds ideal. So why do we need these kind of complex architectures if we can train something that has a fixed cost per token and get the same performance downstream and also in terms of perplexity. Right? So this, you read this paper, it really sounds like we should just throw away transformers and go use state space models. In this talk, I would focus on another way to evaluate language models is look at synthetic tests. So we're kind of trying to characterize the building blocks or the things we should care about that these language models or sequence models should be able to do. So kind of give a mathematical definition for a task that we want the language models to be able to do and try to use it to sort of study the benefits and limitations of different architectures. And just kind of maybe as a side note to try to justify this, and this is, I think, like an ongoing discussion, is like, why do we even care about synthetic tasks? I mean, we have all these benchmarks. We have all these ways to evaluate language models. Why do we do synthetic tasks? So there's something, I think, very nice about the setup is that we kind of understand it completely. There's no noise unless we inject noise into the problem. When things fail, we understand why they fail. When things work, we can kind of hypothesize why they work. We kind of have a good understanding of the model, and we have kind of a mathematical framework for studying these problems because these are mathematically well defined, and then we can kind of do theory, like upper bounds and lower bounds, try to understand, what is the limitations of different models given different amount of compute, and there's kind of something very nice about this. In some sense, when you do theory, you can ask questions, what would happen if I scale the compute of this model? Would it be able to solve this problem or not? Right? Because this is kind of like always a question. Maybe I just need to train a bigger model. Would this solve this problem? And when we're doing theory in these synthetic tests, it's kind of easy to answer these questions, even if you're not running the experiments. This is, I guess, just as a way to motivate studying synthetic tests. So I guess the first work that I'm going to talk about is exactly comparing transformers to state space models. We're going to be focusing on a very specific set of synthetic tasks, is copying sequences from the input context. As I work with Sami Jelassi, David Ranfenbrunner are both postdocs at Harvard, and with Sham. And this will be kind of, I guess, the topic of the first part of the talk. So I'm going to focus, the main task that I'll focus on is a very simple task, almost like a dumb task. I give you a sequence of tokens, and you just need to repeat it again. So a sequence of tokens, some token that indicates that the sequence is ended. You just need to kind of reproduce the same sequence of tokens again. So in itself, it's not a very interesting task. We don't need GPT-4 to repeat the thing that we just gave it. But somehow this is an interesting building block in different tasks that we ask language models to do, such as like in-context learning, retrieval, question answering. You can think of these as kind of variants of copying parts of the input or copying the relevant part. And the related task is retrieval, which is, I guess, in some sense similar to copying. I give you a sequence of tokens, and then sort of a key, which would be another short sequence, a short n-gram or sequence of n tokens from the input context, and you need to complete it, like provide the next k tokens from the input context that appeared after this. Also, a very simple task, and you can see how these two tasks are. Yeah, so I'll start with the theory results. So we're going to prove like an upper bound for transformers, show that transformers are actually good, or maybe this task is somehow a natural thing to do with transformers, but state space models or recurrent models would not be able to solve this task. So we have kind of a fixed dictionary of tokens. We're given a prompt, a sequence of length L, and we need to just reproduce the sequence of N tokens. And we're going to do this autoregressively. So each iteration, the model is generating the next token, and this way we want to just reproduce the sequence of inputs. The model.
Yes, sir. I probably misunderstood what you said earlier in view of this. Did you not start by saying that both these models seem to work equally well in practice, so why do we need one?
Yeah. So it depends on how you measure it. If you take the perplexity, the loss of the model on the training data set, it seems that they both get the same loss. And for some downstream tasks, they seem to both work well. I will try to illustrate how, like, looking at these tasks and this, like, at the end, go back to like specific ways to evaluate the downstream performance would kind of illustrate that there is a significant difference between the models. And even though when you're kind of averaging everything, it looks like they behave the same, when you kind of take this, I guess, synthetic task perspective and study these models, you'll see, like, very stark differences between the models. So it's kind of like a way to poke specific abilities of the model and try to understand, like, the differences. But it could be that when you average everything, the kind of average performance is something like this. Okay. So first, the first theoretical result is we're showing that small transformers can do copying. So small transformers can just reproduce the sequence of tokens that are fed to them. In terms of memory, they don't have a problem because they can always access the kind of entire sequence of tokens in the context. But I guess the point of this result and the point of the construction I'll discuss soon is that there's something kind of natural about doing copying and retrieval with transformers that is kind of maybe baked into the architecture and kind of like a non-trivial. Yes.
So I know you don't want to go into details, but what is it you call a depth-2 transformer with a certain, so dimension is the embedding dimension?
Yeah.
And depth-2 is like both attention and feed forward?
Yes. Yeah. So this is like one block is attention feed forward and 2 blocks is what we need. Okay. Yes. So there's a small transformer. Dimension is like the size or the hidden dimension in the model. And what this result states is that the transformer that we construct can perfectly copy strings of exponential length as long as there are no repeated n-grams, right? So no repeated sequence of n tokens, right? This is, I'll show the construction. I guess it'll be clear why this is a requirement.
But just, I mean, n is any number here. It's not some
Yes.
before, right? I'm just making, it's not like some.
For all n.
For all n. It's not like a transformer or some prime.
No. This for all n. This. And the bigger the transformer is, the larger the n that we can have. And I guess, it's easy to show that if you're, say, sampling from a uniform distribution, the probability of having repeated n-gram decays exponentially with this n. And what this tells us is that for, like, copying uniform strings, we can copy length L sequences of tokens where the transformer is size, the logarithmic in the sequence. So small, very small compared to the length of the sequence that we actually. Yes.
Do you use that tight? Do you think it's possible to do better than that? Or?
Okay. I think there's there's multiple ways to construct transformers to do copying. The specific construction that I'm going to give maybe is not the intuitive one, but I'll try to convince you that this is kind of the natural thing for a transformer to do. So the point here is not to get, like, tight bounds on how to implement this, but to get a construction that somehow resembles how transformers actually solve. I'll try to convince you that, like, when you look at how the transformer actually solves this, this is really what it does. And I guess in that sense it's tight, but maybe you can come up with a different construction that's better, but kind of for our purpose is not going to be useful. So this is not just kind of like just for the sake of proving a theorem, it's for the sake of like giving a construction that actually resembles what happened. And the idea here is somehow like kind of a generalization of the induction head principle that I'm sure a lot of you are familiar with. So, okay, maybe one natural way to do copying, I give you a sequence of n tokens. You need to reproduce it. First, look at the first token, use some like absolute position embedding, bring the first token and the second token, etc. But this is not what we're going to do. Instead, we're going to have this kind of lookup table that maps sequences of n tokens, n-grams, to the next token in the sequence as it appears in the context. Is kind of, you can think of each token constructing this lookup table. And then when I need to reproduce the sequence token by token, I have already the sequence of tokens that are already generated. I can look at the most recent n tokens, find them in the input sequence, and just bring the next token. And if I do this iteratively, this generates a copy of the sequence. And the nice thing about this is I rely only on kind of like local positional embedding, and I don't really need an absolute position. This will turn out to be useful when you're going to get properties like line serialization and things like this. And also you can see that this is somehow like natural to do with transformers, because this kind of induction head mechanism of like mapping keys and queries and outputting the next thing is something that transformers is somehow very good. So this is not just, a theoretical way of doing things with transformers. Is actually trying to build something that is kind of reasonable for transformers to do in natural language, right? So we're kind of relying on this kind of hashing n-grams for the keys and queries, and using this to kind of output the value to be the next token. Really just a generalization of the induction. Yeah.
So right now, I guess you're describing it as like, okay, I can implement it as a lookup table.
Yes.
Would you expect to need tons of data to try and actually learn this lookup table in practice?
Yeah. So I'll show experiments.
Okay.
And maybe this will complete. It's learned pretty fast when you train on this. So, I don't know what tons of data mean. I mean, it's a lot of data, but
like enough data to like learn all the rows individually of this lookup table.
Right. Yeah. So I guess what you're saying is, do I need to kind of like have seen all the possible n-grams to do this? No. So it's basically just realizing the sequence of tokens are the same, and maybe it just, you need to kind of find a mechanism of hashing together sequences of tokens. Okay, it's a good question. I don't have like a good answer on like how many examples you need to see, but intuitively, you don't need to see like all the possible n-grams to necessarily be able to do this operation. But
memorizing the lookup table, because you're just figuring out that you should look back and then choose the next value, so you don't have to ever memorize.
Yeah, it's all like in context. Yeah, you need some way to kind of hash together a sequence of n tokens and then realize that the two things you've hashed are actually the same thing, and maybe you haven't seen them. But maybe, I don't know. I don't have like a good. I don't have any optimization or learning results on this. So it is possible that you need to see a lot of data. I'll show some experiments.
Like just heuristically, if you look at the number of parameters, they don't scale with like all possible n-grams.
Right. Yeah.
So it gives some indication that you're not just.
Yeah, but maybe somehow to learn.
Like,
okay. Yeah.
I was going to say, like, it does seem like there is a dependence on n. So my intuition is that the position-based strategy, like for some large n, becomes simpler than this strategy.
Right. So yeah, I'll try to experimentally show you what this n turns out to be, and then it's not going to be, even a small enough n is already enough to copy policies. And remember that the dictionary can be quite large.
Maybe that's an naive question, but what happens if we have when the n-grams are not correct?
Okay, so in theory, what could happen is you have this n-gram or hash table or lookup table, and then you kind of attend to the wrong n-gram, and then you complete the sequence in a wrong way. Right? I'll try to show you like the kind of performance decays gradually, but yeah, I mean this could ruin the and it does. Yeah.
Does it depend on the number of heads to copy? You might need more heads, right?
Yeah, so we I'm not talking about this, but we do use like multiple heads, and in fact we use like kind of a specialized positional embedding that depends on the number of heads for the construction, and also show that it's useful to use this positional embedding in practice. So we have like different heads kind of attend to like different kind of windows, and this is important for the construction. I think someone mentioned to me that you might be able to get this with less heads or maybe even one head, but I'm not sure. Yes. Okay, so this is a positive result for transformers. They can copy. A negative result, I mean, this maybe should be obvious. If we have a state space model, then for our theory, by state space model, we only mean that there's a fixed state that is being updated. So we have some update rule on the state, and some output rule that maps the state to the next token. And we assume that the state space is finite. So there's like a fixed number of bits that encodes the state. And the result is very simple, stating that any state space model with a fixed number of states will have an error that decays, I guess, exponentially with the length of the sequence. So if you don't have enough bits in your state to encode the entire sequence, obviously when you're sampling uniformly from uniformly a length L sequence, you're not going to be able to get a good loss because you just don't have enough capacity. Okay, so this is very simple proof, and it shows you this gap between transformers and state space models, at least in this copying set. But okay, who cares? I mean, maybe the answer is sure. If the size of the memory of the state space model is small, well, then it cannot fit the entire sequence into the memory. But in some sense, you know, okay, we'll just train a bigger state space model, and we'll be able to fit the sequence into memory, and then this solves the problem. But then there's a question of optimization. Okay, maybe both models can fit the sequences into memory, but you know, how long does it take you to train? So maybe this also relates to the previous question. So here, okay, we have experiments. We don't have a theory, but what we do is like comparing state space models and transformers on the synthetic copying task. And blue is transformers with different choices of positional embedding, and red here is the Mamba model. And you can see that even in the case where after a while they both converge to like 100% accuracy in solving this task, the transformers train much faster. It's like 100 times faster than the Mamba models. So, you know, there's no expressivity gap. So they can both fit the sequence, and they both do fit the sequence eventually, but it takes transformers much less iterations or examples to solve this task. So they're kind of much more efficient learning. Yeah.
In terms of like absolute time, like what was the time difference? Like for example, with the SSMD.
Yeah, I think you know I'm not sure, but I don't think that in training the state space models don't have like any advantage.
Oh, okay, thanks.
Yeah.
Are you differentiating here between samples and training runtime? I mean,
No. So this is online.
So, but do you think that the issue here, I mean, I don't know if you have some insider experiments, that the issue here is really training samples or run? Is it that they really require more samples because the
I don't know.
Or is it just
I don't know. It's a good question. It's kind of in the online regime, so samples is runtime. I think they need more samples, but like just for kind of maybe parameter counting. But I don't know. Like, it's a good question. We don't have any theory. It's just.
I mean, you can answer this with the experiment, right? You do.
Right. Yeah, we didn't do it.
Full passes or something. Good question.
Just to clarify, so there's no capacity gap between LSTM and Mamba. So the gap between here is just training.
Yeah, so this is LSTM actually is not converged at all, but Mamba and so Mamba is the red line here, Transformer is the blue line. So they both converge to 100%, right? So they can both solve the problem, right? But it takes the Mamba model a lot longer.
So I guess you were saying that it's not a capacity issue.
Yeah, it's not a capacity because we see that it solved the problem.
But this, I mean, this is presumably for specific length.
Yeah.
But and with when it's either uniform or you made sure that there's no n-grams, right? But if you try to like challenge them, is there a big difference? I mean, now it'll depend, I guess, on what the models are, right? But if you use a model of comparable, like a computational number of parameters, then and you pushed it, would you see a gap?
Yeah, so this is I think even giving advantage to the Mamba model in terms of number of parameters, but I'll show more experiments and maybe by the end you'll be convinced there's like a real gap. Okay, so optimization, even when there's no like expressivity gaps, there's a problem in terms of optimization speed. Another thing that we might care about, and maybe if we don't care about the speed of optimization, is length generalization. So we showed length generalization would simply mean that I'm training on sequences of length L and then trying to extrapolate to sequences of length larger than L. And we showed that transformers can do copying of strings that are size exponential and that are exponential in their size, and state space models need to be kind of linear in the size of the sequence that they can copy. So theoretically, you can imagine that if we're taking the state space model to be big enough, it's able to learn to do copying on the sequence length that can fit in memory. But if we try to extrapolate, try to achieve length generalization, this would actually not work. And indeed, we're training transformers and state space models to do copying. We see that they both in distribution, so here the red line marks we trained them up to length 50. In distribution, they both do very well. They get to 100%. But when we move out of distribution, Mamba models or the LSTM drop in performance and very quickly get 0% accuracy. And the different variants of transformers are much better in extrapolating to longer sequences. Again, this sort of tells you that they learned the right mechanism. Just as another note, so I described this kind of construction of doing copying with transformers. Now let me try to convince you that this is what they actually learn in practice. So what we do is the following experiment. We train them to do copying, and then at test time inject repeated n-grams into the sequence, so kind of force sequences that have repeated n-grams in the context. And if you're just doing copying based on positional embedding, there's no reason that this should hurt performance. You're just mapping the next token based on where it's located. But here we see that as we increase the size of the sequence that is injected into the context, we see the performance drop. So you can kind of maybe try to estimate from this that maybe they're doing hashing of n-grams where n is like 5 or something. And when the size of the injected sequence grows, you can see that the performance drops to kind of like trivial. This sort of tells you that our construction really captures what really transformers are doing. So it's not just like theoretical. Okay. Yeah, let me skip this. I guess I'm late. So just to move from kind of synthetic experiments of models trained from scratch, now let's compare models that are trained on actual language data. So these are Mamba models versus transformer-based models trained on language data, basically the same data set trained for the same time and kind of matching the number of parameters. So here we'll let them do copying by simply giving them natural language strings repeated a few times, and then the first word from the string, and they need to complete it. And you can see that transformers are quite good at this, even in the cases where the number of tokens is quite large, and state space models are much worse. And again, this is, sort of like a natural task, and you don't see this, if you just look at the perplexity. This is kind of like attacking this particular property of being able to copy. And same for retrieval. So we give them the kind of phone book task. We give the model a phone book in context, and it needs to retrieve the phone number of a particular individual in the phone book. And transformers are very good at this, and state space models are quite bad when the size of the phone book is large. And finally, we're doing kind of maybe a real language task where we're giving a question answering task. You get a paragraph and need to answer a question. It's basically retrieval of some information from paragraph. And as the number of tokens in the paragraph increases, we can see that the performance of the state space model decreases, but the performance of transformers pretty much. So this is kind of, bringing all these intuitions and copying into kind of the more real world setting. Yeah, so just to summarize this work, just so I have like some time to talk about the next work. So we show that transformers are better than state space models or RNNs on copying and retrieval tasks. We show both theory results, synthetic experiments, and also experiments on real pre-trained language models. And maybe kind of the takeaway here is really what we want is sort of like a hybrid model that maybe combines the best of both worlds from transformers and recurrent. Okay, so let me move to the next work that is kind of building on this same ideas of length generalization using a copying test. But now we're going to focus on length generalization in general, and I'll try to show how transformer is kind of good at or could be trained to do length generalization on kind of a wider variety of tests. And this is a work with basically the same people, and Kaing, who's Harvard. So again, the length generalization problem, I show you a string of length L, and I want you to generalize to longer strings or longer problems. And this has been studied a lot in the context of kind of algorithmic problems or arithmetic problems. Multi-digit addition is something that's been a lot of people worked on recently. I trained the model to do multi-digit addition with 50 digits, and I wanted to do addition on kind of longer strings, and maybe like kind of to motivate why this question is even interesting. So like one, from a kind of practical perspective, it's cheaper to train models on short sequences. So if we just train a model on a short sequence and get performance and good performance with long sequences, is kind of just practically a more efficient way to do learning. And second, if we get length generalization and these different problems, maybe it implies that a model is sort of like learning the right algorithm, learning the right solution to the problem. And what we're going to leverage here to do to achieve length generalization is basically this kind of chain of thought or scratchpad technique that was like mentioned by various people yesterday. So instead of just training the model to output the solution to the problem, which is usually a hard thing for the model to do, we're going to train it on a sequence of steps that kind of encode the solution to the problem if we kind of break the problem apart to kind of step-by-step solution. And this usually makes things easier. So in the copying task, we can, in the addition task, we can break the addition problem into kind of multi-step algorithm for solving the addition. And one interesting observation that really every step in the addition algorithm just copying the previous step plus a small modification to the next step. And another observation is really any algorithm can be written in this way. So this is not just a special property of addition. I try to convince you really this is just a general phenomenon, and really any algorithmic task can be broken down into a sequence of copy and small modification. And this is really related to, I guess, some things that people talked about yesterday. Any algorithm can be implemented by a Turing machine, and we can really convert any Turing machine into what we will call Turing program, that is just writing the state of the Turing machine over and over, when the difference between two lines in this kind of chain of thought would be the operation of the Turing machine between the different states. So we have the state of the machine at line t plus 1 would be the state of the machine after one operation. And these all involve just copying like most of the string and then like doing small modification to the string where the head was and where the operations were. Yes.
Sorry, so we assume the modifications are on the order of like a little while.
Yes. So this, like, generally how Turing machines operate, the head is in some position, and it either moves left or right and changes the symbols under the head. So everything is like kind of in an O1 window of the head, and then like everything is kind of local. So you're copying most of the things, and then like change only the state. So any algorithm can be encoded in this way. Maybe this is a very inefficient way to encode algorithms, but hopefully you're convinced that you can convert any algorithm to a Turing machine or a Turing program of this form. And now the question is, can transformers actually implement this formulation of the algorithm? And we showed this by generating a nice RAS program. So if you're if you're not familiar with RAS, this is sort of like a programming languages that is aimed to capture how the operation of transformers are built, and there's like multiple variants of this programming language. We choose a particular variant that is kind of doesn't allow us to do kind of weird operations on positional encodings and on indices, and we can show that for a nice enough Turing machine, we can construct a RAS program that basically simulates this Turing machine and generates the Turing program of like the runtime of the machine for exponential number.
We have a proof that any RAS code can be simulated by transformers?
Yes, for some variants of RASP, yes, and I guess we're not entirely rigorous in verifying that the program here is falls into one of these categories, but basically the answer is yes. If you the variant of that. So this is a nice, okay, I'm not trying to prove, but it's actually code. This nice way to show proofs in this language. You can just write the code and see that it generates the thing that you want to generate. So this is really a kind of way to do programming this language. Is very fun to do. And I guess the benefit of doing this construction over other constructions that are showing like universality of transformers is that somehow the way that we construct the RAS program in a way that doesn't rely on positional embedding makes it kind of nicer for achieving like generalization, which is often not guaranteed when you're kind of using absolute positional embedding. So I'll end with some, yes?
I guess just, you had that no repeated engrams assumption on the previous slide.
Yes.
Like, how restrictive was that in practice?
Yeah, so again, like the no repeated engram, basically everything that goes on here is very similar to the construction of the copying. And if you have repeated engram, you're going to fail in copying, and therefore you're going to fail in executing the Turing machine. And in practice, we actually see this. So even in addition, when we're implementing this, if we have kind of repeated sequences of digits and the number, then this actually fails. But you can imagine that if you're sampling uniformly and the n is large enough, then this is not very restrictive. Otherwise, if the input is not uniformly sampled, then this can be a restriction. Yeah, so just some experiments. So we're training transformers to do length realization using this kind of Turing programs approach. We actually write down the kind of full trace of the algorithm that does addition. And indeed, you can see that with the kind of correct choice of positional embedding, transformers trained in like length 50 addition are doing very good at this and extrapolate to much longer strings. We can also get this for a more complex task of doing multiplication. So here we have n by 3 or n by 1 multiplication. So the sequence, we multiply sequences of n digits by sequence of 3 digits, by 1 digit. And we can see that, again, we can write the algorithm for doing multiplication in this setting. And again, we can see that choosing the right positional embedding for transformer, you get this very nice length realization where we train up to length 50 and you get like beyond 100 digits. This is like exact string matching with the right answer. Okay, so maybe try to take this into kind of a more advanced algorithm, maybe something that's a bit different than the arithmetic problems that people are trying to achieve length realization on. So here we're actually trying to simulate SGD, And what we're going to vary here is not the number of digits in the number, but actually the size of the data set. And we're simulating, it's a very simple setting of SGD. In R2, you're doing basically mean square error and try to simulate the steps of the SGD and to come up with the kind of final weights of the thing that you're learning. This is somehow maybe resembles in context linear regression that people have studied in the past. But here we're, again, like kind of writing down the states of the Turing machine that would execute this linear regression simulation. And again, we can see that if we train up to size 50 data sets, we can extrapolate to much longer data set sizes. And this is kind of, I guess, the first algorithms is in some sense very different than what people have studied in the concept of length generalization. You can see again that we can get very nice length generalization even in this kind of very different type of model. Yes.
So how do you tune that? Have you tried to add new how do you
Yeah, so we're basically, I think a lot of parameters work, but we're basically just trying different numbers. Yeah, and I guess the final experiment, this is sort of trying to convince you that this length generalization ability is somehow more general than specific algorithm, is like, can we actually achieve length generalization on any possible algorithm? So any possible algorithm you can write down as a Turing machine, and you can execute the steps of the Turing machine and show that we achieve length generalization. And we do this by basically sampling random Turing machines and asking the model to map between one state of the Turing machine to the next state, and again, try to measure this length generalization. So train it on states of size 50 and let it extrapolate, and we can see that for different choices, choices of Turing machines, we actually get very nice extrapolation into like much longer. So again, this doesn't prove anything, but it suggests that this thing could be as general as you want, and really any algorithm, if you gave me the right chain of thought, you can get length generalization. Yes.
How much longer is the Turing machine version of these problems than were made?
Yeah, so it could be very very long.
Specific example, like in your experiment.
How much longer in what sense? Like how long is the context length? Yeah, I mean, so you can do the math, like it grows for. I guess most of the problems that we're doing, it grows like linearly in this sequence length. So this could be quite long.
Like just one number, like how you in the like I don't know what you showed there.
Yeah, it could be in the thousands, and we train it with kind of sliding windows. So we're not fitting everything. So if you'd wanted to fit the entire thing in the context, it would be very hard to train. Just computationally. So we're kind of slicing this into a sliding window, and then like when we're doing inference, we're also doing this sliding window, but it's like thousands of tokens. Yeah, yeah, it's like a very inefficient way to encode the problem. So we're not trying to argue about it. Yes.
But in chain of thought, you're giving each step of the Turing machine,
Yeah.
like the computations. The chain of thought itself is like really long.
Yeah, well, the chain of thought is kind of, we give like sequentially the states of the machine. So it's the size of the chain, the size of one line times the number of steps. So it's not really a Turing machine, right? It's kind of, for all these algorithms, we've come up with something that kind of resembles the operation of a Turing machine. But yeah, generally it's going to be quite long, and it's much longer than the, I guess, more efficient construction of like that, I guess, not you referred to and other people have shown, that you're just showing the diffs of the Turing machine. The problem with just giving the diffs is that length generalization would be harder to achieve in this case, because you really need to rely on absolute positions to
So why do you need absolute positions for that?
because you need to somehow know, given the position of the head, to attend to the right position. And
The only thing you need to know is what's the last one. That's a bit. That's
the last one, yeah, but
that's much better. That's not an absolute position. You have to find the one. You have to. I mean, that's what I think of the standard induction, right? You find the last occurrence.
Yeah, but you need to somehow attend to the position of the head you need to know what is the kind of token, the sequence of tokens that. No, you're not convinced. We can talk about this later, but I think there's like you're gonna have some problems if you want to get generalization with this kind of more sparse encoding of information. But we can talk about this later. Yes. Okay, sure. Yeah, I'll so yeah, just I guess to summarize the second part of the talk. So we're basically trying to achieve length generalization with transformers by kind of leveraging the property that they can do copying good and length generalize on the copying operation, and we can show both with theory and with some nice experiments, so we can actually get length generalization much more complex problems. Yeah, I'm done. So if you have any questions, either now or.
So this, I guess the results on the Turing program seems to say that like, okay, if you have any problem in P, then there exists some transformer that like with chain of thought, where the chain of thought is like your new description of the Turing program can like output the right answer. But I think in maybe like Will's talk yesterday, there's even with chain of thought, like the set of, I don't know, like things that you can represent is still in one of these like restricted complexity classes like NC1 or something. So I was curious like what the caveat was or what the mismatch was.
Well, I guess it's only a question of how you restrict the length of the chain of thought, right? So if you let the chain of thought be polynomial in the input sequence, then there's no there's no problem to. I guess this is not equal.
Yeah. So the figure I showed was for linear chain of thought. If you have polynomial steps.
Then you can do anything.
So for length, to get length generalization, it's not enough for you to show that there exists a REST program for that. You have to show that in some sense that's the shortest. That there's no and it's not just a REST program because maybe that's the shortest REST program, but actually there's a smallest transformer. So do you have any ideas for how we can actually reason about that and really argue that by training on short things we will be able to generalize? Is what you learn will really be this thing that generalizes?
Right. Yeah. So I guess there was one question like whether the thing that generalizes is the shortest RAS program, and then a second thing whether you learn the short RAS program. And I guess like both of these things we don't have an answer to, but what we can do is sort of verify that the solution a transformer learns is kind of resembles this again by querying it with like I guess injecting repeated patterns, and we see the same behavior in these cases. But yeah, I mean this is potentially it would be interesting. We don't have like result.
So I think in your experiments you showed that hard alibi is very important.
Yeah.
I guess then should I think of this as if you're using hard alibi, then you were effectively putting a capacity on this like space time because you can only see within your alibi.
Yeah, so I guess it's kind of a way to localize the positional embedding and kind of to force you to allow you to learn this kind of local engram hashing that is very important. Again, for at least for the copying part, we see that the transformers learn to do copying even if they're just trained on natural data with kind of standard positional embeddings. There's also kind of variants of positional embeddings or kind of like sliding window attention that sort of resembles this behavior, and maybe this kind of help you. I would say that like I don't think it's definitely necessary to have this like particular positional embedding if you're trained on natural language. It's sort of like you learn this ability of doing like kind of n-gram induction heads just from training on natural language. I think there's like several works that show this can be achieved with standard positional embeddings.
So if you only have a constant sliding window size, that when you how can achieve that generalization? Because when you input that becomes longer, like you need more memory, and also go beyond that, you can generalize.
Yeah. So what I was trying to argue is that indeed it doesn't work for like infinite length, but for exponential length, this kind of fixed window size is enough. So the length of the string that you'll be able to copy is exponential in the size of the window that you're going to fix. Right. So it's it doesn't allow you to copy arbitrary length strings, but it's exponential in the slider models.
Okay, I think we should probably take the rest of the questions off. Right?